Hello Chem 1B, this is chapter 17, lecture video 6, and we're going to be continuing our calculations for a weak base strong acid titration. And the next type of calculation you might have to do for this is the pH at the equivalence point. Now, when we're thinking about this, the equivalence point, basically all of our weak base has reacted with the strong acid, let's say HCl. So neither HCl nor A minus are present in the solution. All that remains is the conjugate acid of A minus and water. So at this point we have a weak acid solution, and we need to do the calculation for pH using the weak acid equilibrium. HA goes to A minus and H3O plus. The pH is going to, as always, be given by the H3O plus concentration, which we can get from an ice table using the weak acid's concentration in the solution at the equivalence point. We need to use the Ka value here because we're using a Ka equilibria to solve the pH. Again, the weak base is gone. We cannot use the Kb value that we were given to solve this equilibrium. We need to determine the Ka for the conjugate acid. This also tells us that the pH of the solution, because we have a weak acid present at the equivalence point, is going to be less than 7. This is significantly different from the calculation for a strong acid, strong base equivalence point pH, which would be 7. For a weak acid, strong base, it would be greater than 7. For a weak base, strong acid, as in this example, it's going to be less than 7. And this is due to what's present at the equivalence point. In this case, it's HA is present at the equivalence point of our titration, which is a weak acid, so we'd expect the pH to be slightly acidic. Again, I can't stress this enough. The only time the pH is equal to 7 at the equivalence point is when we have a strong acid, strong base reaction going on. So we're going to fill in this point now on our little graph, continuing where we left off last time. Again, we need to do a couple things to calculate this. We are going to use the moles of the strong acid added, the moles of the weak base that we started with. These are going to be equal, and basically we're going to form HA from this. We can calculate the moles of HA formed using the volumes that were required to get to the equivalence point, and what we started with, we can get the concentration of HA. Once we have the concentration of HA, we use the Ka value and an ice table to solve for H3O plus, at which point we can get the pH. So let's do an example. All right, we're going to use that same data that we had from last time. What is the pH for a titration of 25 mils of 0.126 molar NH3 by 0.287 molar HCl at the equivalence point? Kb is 1.8 times 10 to the negative 5. So we need to first do an ICF table, right? So we have NH3 aqueous reacting with HCl, also aqueous. This goes to one-way arrow, NH4 plus and Cl minus. And again, don't really care about Cl minus because it's a neutral ion. The NH3 and the HCl are what we really care about here. So I need to calculate my moles of each of these as we did in the last lecture video. And so the moles of NH3 are 0.00315. Now we're at the equivalence point. So by definition, we know the moles of HCl have to be equal to the moles of NH3. That's kind of the whole point of an equivalence point, which you should have learned in Chem 1A. Now initially we have 0 NH4 plus, and since these are equal to each other, we're basically subtracting them both off from each other. And we get 0 of both of them. Now we add 0.00315 over here, so we have 0.00315 moles of NH4 plus. Now at this point, the NH4 plus is going to do what weak acids do. They're going to dissociate in water to form NH3 and H3O plus. And at this point, we need to use an ice table to solve this problem. But the problem is this is a Ka, and we were given the Kb. So I need to calculate what the Kb is for NH4+. We can do that using our equation Ka times Kb is equal to Kw, right? So I know that Ka times 1.8 times 10 to the negative 5 is equal to 1 times 10 to the negative 14, or that Ka is equal to 1 times 10 to the negative 14 all over 1.8 times 10 to the negative 5, which equals 5.56 times 10 to the negative 10. Okay, so we have our Ka. Awesome. Now, one of the common mistakes I see students make here is one, they use the Kb instead of the Ka. Well, we just fixed that issue. The other is they use this value and they plug it right in here. That is not okay. The reason why is because this is in moles. And if you remember from chapter 15, the only thing we're allowed to use in ice tables is molarity and atmosphere. So we need to calculate the molarity of NH4+, right? So we know NH4+ concentration is equal to 0.00315 moles divided by total volume. But do we know the total volume? We know we have 25 mils of NH3 was initially present, but then we added a bunch of HCl. We need to figure out what volume was required to reach the equivalence point, right? So I know that I used 0.00315 moles of HCl at the equivalence point, so I can use that value and divide by the 0.287 moles of HCl per 1 liter and get liters, right? So if I do that division, right, I get that I added 0.01098 liters, or 10.98 milliliters. All right, so now I can get the total volume because it's this plus 25 mils gives me my total volume, which gives me in liters at least 0.03598 liters. I can then take my moles of NH3 and divide by that, and this gives me a concentration of 0.0875 or 0.76. So now I have my concentration. I can put that here. I don't care about water. It's a pure liquid. We don't have any NH3 anymore. We don't have any H3O plus initially. We know X plus X plus X, 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 0.876 minus X. It's a terrible one. All right, now we can set this all equal to the Kb that we just calculated, right? So 5.56 times 10 to the negative 10 is equal to X squared all over 0.0876 minus X. I am definitely using the 5% rule here. I can solve for X. And I get that X is equal to 6.98 times 10 to the negative 6 molar. pH is just going to be equal to the negative log of that. And if we do that out, you get that the pH here will be equal to 5.16 as our pH. So if I just take this and plug into there, that will get me that answer. All right, so if you have any questions, let me know. Let's move on to the last region of the weak base strong acid titration that you might see, and that is the excess acid region. And really, this is a neutralization step followed by the determination of the H3O plus present in the solution. After the equivalence point, all we have left present in the solution is weak acid and strong acid. And if we have a weak acid and strong acid mixture, we know that the pH from the last chapter is really only dependent on the strong acid. So the first step here, as with any titration problem, is we need to write out our ICF table and do our calculation. Still don't care about the Cl minus. And so we have our ICF table. We know we have 0.00315 moles of this initially. And now we actually do need to calculate the moles of HCl because we've added 15.3 milliliters. We need to figure out, based on this concentration, that volume, what moles of HCl we have. And if we do that calculation, we get 0.004391 moles of HCl. We're then, I'm just going to get rid of the 1 so that we still have 0.3 sig figs. So I'm going to subtract off my limiting reactant. In this case, it's the NH3 because we're past the equivalence point. We also get 0.00315 of that. So we have 0 left of the NH3, and we have 0.00124 moles of HCl and 0.00315 moles of NH3. Now, HCl is a strong acid, NH4 plus is a weak acid. We really do not care about this value. We really only care about this value. Now, I need to calculate my HCl concentration to get pH, because it's the negative log of that concentration that will get me the pH. Well, I have moles, so how do I get this? Well, I take my moles, 0.00124 moles, and I divide it by the total volume in liters. Well, that total volume in liters is going to be 30.3 milliliters, right? Because it'll be 40.3 milliliters. So we have 0.0403 liters. 15.3 mils plus 25 mils gives me 40.3 mils. And this will get me my concentration here, which will be equal to 0.0308 molar. We just need to take the negative log of that to get our pH. And if we do that, 1.51 is our pH of this solution at this point in the titration, which makes sense because we're in the excess acid region, so there's a acidic pH. All right, so let's continue our graph here. So if you look at this whole thing, our initial pH is just the weak base present in the solution. We can solve that using an ice table and Kb to get OH minus, then get pH. Any point after the initial pH, we can solve using a neutralization step and then followed by Henderson-Hasselbalch. At the equivalence point, we have to figure out we do our ICF table, neutralization step, figure out how much HA was formed, use the Ka and the concentration of HA present to get the H0 plus concentration and get the pH. After the equivalence point, we have the excess acid region. We're going to do a neutralization table, figure out how much strong acid is still present, get the concentration of it, take the negative log to get the pH. And this is how we do our calculations for a weak base strong acid titration. They're very, very similar. The main two differences are here, and here. The buffer region tends to be the same thing. In a weak acid, strong base titration, you're starting down here because you just have a weak acid by itself. You use a Ka, H0 plus. In the buffer region, right, you're going to use the Ka and, a neutralization step, and then Henderson-Hasselbalch. At the equivalence point, you use the Kb because all you have left is weak base, get the OH minus concentration, take the negative log, get POH, then get pH, and in the excess base region, we figure out, use a neutralization step, figure out how much strong base is still present, get the OH minus concentration, POH, then pH. So we have one last little thing to talk about before we move to the next lecture video, and that is, okay, what about titrations involving polyprotic acids? They're kind of special. Like we learned in the last chapter, polyprotic acids ionize in steps, right? Each proton goes away in one step. Now, the number of ionizable protons, like for instance in H3PO4, we have 3 ionizable protons because, there's a 3 here. That's how many equivalence points this titration would actually have if I titrated this acid with a strong base. And we'll see that on the next slide when we do oxalic. Oxalic acid has 2 ionizable protons because there's this 2 here. And that means when we titrate it with NaOH, a strong base, we're going to get 2 equivalence points. The first is when we form the HC2O4 minus, and then the second is when we form oxalate. And if we look at that titration, you can kind of see it looks different than the previous curves we just talked about, right? We have like another kind of step in our staircase almost, right? Now, like I said before, at half the equivalence volume, our pH is going to be equal to pKa. In a polyprotic acid at half the equivalence point, sorry, that's not half, that's the first equivalence point. At half the equivalence point here, our pH is going to be equal to pKa1 because that's the first ionizable proton going away. The second equivalence point is going to take the same amount of volume as the first, so this would be 50 mils here. At half that second equivalence point from the first, halfway between the two, we reach again halfway to the next equivalence point. Well, pH is now equal to pKa2 because now we're talking about that second equilibrium occurring. This region is the excess base region. All right, so if you have any questions, as always, discussion session is the best way, and then email is always available as well.